Something called valence shell electron pair repulsion theory. From now on, I'll only call it VSEPR. So valence shell electron pair repulsion theory. And we use valence shell electron pair repulsion theory, VSEPR, to determine shapes of molecules. Right, so for a long time, you've been able to draw the dot and cross diagrams, the Lewis structures, if you like, of simple covalent substances like carbon dioxide and water and hydrogen and all of these things. But you might have noticed that when I'm drawing things like water, I give it that shape, put the lone pairs on as well. Or when I drew beryllium chloride yesterday, I drew it that shape. Or a better example, I drew carbon dioxide, I always draw it that shape. So there's a reason that we draw things with certain shapes, and that's because we know what shapes molecules are, and there are a number of ways of explaining the shapes of molecules. Right? Some of them are more advanced than others, and one way of explaining the shapes of molecules is this somewhat simplistic. In other words, it's not completely true, all of it, but the somewhat simplistic idea of valence shell electron pair repulsion theory, which is a way of explaining the molecules, the shapes of a whole bunch of molecules that you need to be familiar with. And that's the level we go to at IB level. We're studying standard level bonding. We will move on to higher level bonding next year, where you'll look at more complicated molecules, and there'll be some other things to add to the shapes we do today, but it'll be using the same theory to underpin it. So let's just get on with it. So the first thing you need to be able to do with valence shell electron pair repulsion theory is to draw correct Lewis structures, like we've been doing. It's really important that we can draw things like methane and water and carbon dioxide correctly, or you cannot get this right. Okay, so that's why we've been practicing that a little bit over the last couple of lessons, and you need to keep practicing to be really confident about it. But this theory is all about the idea that electrons are negatively charged, right? And as I've told you many times, a lot of chemistry is to do with the fact that that chemistry is entirely to do with, or massively to do with, electrostatics. Okay, so electrons tend to, and nearly always exist in pairs, either we call non-bonding or lone pairs, like the pair of electrons on there or on the outside of the chlorines, or they are bonding pairs. Covalent bond, you can all define, and we practiced it yesterday. So a bonding pair of electrons, shared pair of electrons between a hydrogen and oxygen atom in this case, or hydrogen oxygen nucleus in each case. So electrons are negative, we've got pairs of electrons. Those pairs of electrons that are happily sitting together, they repel one another, right? They don't like being near one another. And the fact that those pairs of electrons, this pair of electrons, this one, this one, this one, don't like being near each other, we can use it, you need to concentrate folks, we can use it to explain the shapes of the molecules. So what we're going to do in today's lesson is just work through the most common, or the shapes that we need to know for IB, and try and find some examples of each one. And we're going to start with linear molecules. And the example we're going to use for linear molecules is the one I've just done above, which is beryllium dichloride. Okay, so as I go through this this talk, if you like, I'll identify for you some rules of the game, if you like, some rules of this that we're going to do, that we need to know. But I'll do it bit by bit and as we go along. So the idea is that electrons are in pairs. We want to kind of understand what the shape is around the central atom. The shape is around beryllium. So if this is a maths lesson, it would be that we've got 3 points, or vertices if you like, and we want to know the point, we call them A, B and C. We want to know the bond angle and the shape around B. Okay, so we can draw an angle there. So that when I say what's the shape and the bond angle, the ABC bond angle, it's the bond angle around B, or in this case CLBE CL bond angle. Right, so we talk about linear molecules like beryllium chloride. So why is it linear? What's going on? So what you need to be able to do is first of all know the answer, which we'll hopefully pick up as we go along, but you also for this need to be able to explain it. So the best thing I can do now is explain why beryllium chloride and other molecules are linear, and then that'll kind of deal with all of it hopefully. So there are, and you'll see that we'll use the same approach to answering questions every time, around that beryllium, two bonding pairs of electrons. And we'll start to notate, we'll start to simplify this a little bit as we speed up, two BPs, two bonding pairs. And we also need to look to see if there are any lone pairs or non-bonding pairs on the beryllium as well. And our Lewis structure clearly shows that there aren't any, and we did this yesterday, we know how to do that. So 0 lone pairs on beryllium. So we can say 0 LPs, right? And then we consider what shape the molecule must be as a result of it. So to do that, what we're going to consider is the total number of pairs of electrons. So we're going to add together the bonding pairs of electrons, which is 2, and lone pairs of electrons, which is 0, and say there are 2 electron domains. I'm getting to the explanation in a minute. So there's 2 electron domains around beryllium. Okay, so we might be picking up marks along the way here by saying how many BPs, how many lone pairs, and how many electron domains in total there are. Right, just for a moment, then I'm going to pause the video and do some acting. So, 2 electron domains about beryllium, and best shown with balloons, but I did it with arms to show that those electron domains want to get as far away from each other as they can. And so what we say in an exam here is the the electron domains move to positions of maximum separation. You can say minimum to minimize repulsion, or positions of minimum repulsion. In other words, they get as far away from each other as they can, and that means that the geometry that we're talking about, the shape around the beryllium, so this is what we call the electron domain geometry, this is a word you have to learn how to use correctly, is linear, right? That's what we said at the top, linear. So, and the bond angle which in this case is a CL bond angle, is 180 degrees, right? So it's 180 degree, and if I just try and keep it on the page up here, that bond angle there is 180 degrees, right? I'm expected to know that. Right, I'll just pause that for a sec, let you catch up. Just to clarify why I've called it the the CL bond angle, is because if your teacher was giving you an ABC triangle, they wanted that angle, they would call it the BAC bond angle, the angle around the central of those 3 atoms there, all right? Right, so it's not the only linear molecule that you need to be aware of. There might be others, but there's one particular one that you want to be aware of, and there's a key point here. So next one I'm going to talk to you about is carbon dioxide, which I've already given away by its picture is linear as well, so 180 degrees up there. So carbon dioxide is very similar, and most of this stuff you just copy and paste, so I can't be able to write it all. But the key thing here is, in VSEPR theory, treat double bonds and triple bonds as if they are single bonds. I'm not going to get into all that. We get into in high-level bonding next year. We'll look at really what a double bond properly is and what's going on there. But for VSEPR, we just treat it exactly as if it's a double bond. Treat it as if it's the same as if it's a single bond. So again, around to the OCO bond angle and everything that we were talking about before is exactly the same. So 2BP, 0 lone pairs, 2 electron domains. So electron domain geometry is equal linear. It's exactly the same as before. There's no difference at all. I missed something else, up here as well. So even though we said the electron domain geometry is linear, we are going to also say the molecular geometry is linear. The moment they're the same thing as each other, that changes when we start adding lone pairs. So just for now, stick with me and it will make lots of sense when we get there. So the electron domain geometry and the molecular geometry for this one as well are both linear. I'm going to give you one more example, and I'm not going to explain it this time because it's exactly the same. Really common example are carbons that have a triple bond. They are also 180 degrees. You've got 2 bonding domains, 1, 2, treat the triple bonds if it's a single bond. We've got no lone pairs on carbon, and so we end up with a linear molecular and electron domain geometry for carbon dioxide, alkynes, and BeCl2. All right, we're going to move on. Next shape we're going to do. The next shape we're going to do is a word, a sort of term that will be new to you, and you'll have to learn this. And I'll practice it with you a lot in class, and we'll hopefully have time to practice it at the end of the lesson if we get time. But trigonal planar molecules is the next thing. So trigonal planar. And you might remember yesterday we learned how to draw BF3. It could equally be BCl3, BH3, or it could be aluminium trichloride as well, which has got a covalent structure, but they're all exactly the same as each other. Okay, so you might remember the dot cross diagram, the Lewis structure of BF3, and this applies to, as I say, also BH3, BCl3, AlCl3, all the same sort of thing. Okay, the boron in BF3 is electron deficient, we learned. In other words, it's only got 6 electrons. It doesn't follow the octet rule. The octet rule kind of breaks down a bit when we look at IB level. I'm going to move to a clean bit of paper because it looks like a mess. So I'm just going to carry on where I am. I'll leave that there so you can see it, but I'm just going to move to a clean bit of paper from now on. So there's BF3, drawn horribly. No lone pair on the boron. So we go through it exactly the same approach that we did before. You'll get very used to this now. So we talk first of all about the number of bonding pairs. How many bonding pairs are there? Show me with fingers how many bonding pairs there are around the boron. Yep, so 3 BP. How many lone pairs are there on the boron? Show me with fingers. Good, 0 lone pairs. So how many in total? How many electron domains are there in total, please? 3 electron domains. Good. Now, I haven't got balloons because I was too lazy to get balloons. But balloons work really well, and there's lots of videos that show this being done with balloons. But I'm going to do it with pens here. that in order for those electrons to get or those pairs of electrons in those electron domains we've been talking about to get as far away from each other as they can, they moved. Oh, this is terrible on the video, but there is a linear. Sorry, it's a planar structure. It's flat. Okay, so it's a flat structure, and the pens or the electron domains move as far away from each other as they can, and so it's what we call a trigonal shape. So they're each pointing out at 120 degrees from each other on a circle. Right, so that's what we need to know here. So the 3 electron domains. Let's get rid of that now. And so what we end up with is an electron domain geometry equals trigonal planar. And the molecular geometry is also, because there's no lone pairs, the same, so it's also trigonal planar. Trigonal planar. You will have to learn these. We practice them lots in class, but you need to practice them at home as well if you're really going to get good and learn this stuff. Alright, so what we also need is the bond angle, so we call it the FBF bond angle. So that's any one of these bond angles. I shouldn't have drawn it like that at all. That's a horrible picture. I should have drawn it like I did it in the first place. The lone pairs on the fluorines, by the way, have no effect on the shape. They're miles away from each other. But that bond angle there is 120 degrees, right? Another example when trigonal planar comes up a lot is when we've got a carbon that's got a double bond. So for example, we've got ethene, which looks like that. You'll now know why when I draw ethene, I always draw it like this, with the correct shape there. So we've got, that's exactly the same for the same reasons. We've got 3 bonding pairs, no lone pairs, etc., etc. And again, we need to say that we treat double bond like single bond, just like we did when we were looking at carbon dioxide on the previous page. So we treat ethene the same as we do chlorine, because we can treat the double bond as if it's a single bond. Okay? Any questions at all? So a good clarification question there was, when I say electron domains, I mean pairs of electrons. We will start to look at next year what those pairs of electrons look like. They exist in regions of space together. I'm going to go get a model to show you what that looks like, but you don't need to know this till next year. But one second, anything else? Just a final quick example for you is when you've got something like this molecule. We haven't studied this kind of organic molecule yet, but again, we've got exactly the same idea. The HCO bond angle in this molecule, which is called methanal, is 120 degrees for all of the same reasons as before. So it's another example for you. All right. So whenever you see a carbon that's got a double bond on it, it's going to behave like that. It's always the same. All right. Should we move on? Leave it there just in case you need it. I'll just carry on up here. So we're going to next look at a word you have heard before and are familiar with. And while I'm at it, actually, I'm just going to point something out to you. You've all seen this model of graphite before when studying GCSE, and we'll look back at graphite and diamond again in this topic. But in graphite, can you see that the carbons are each connected to 3 other carbons? So each of these is that trigonal planar. That's why the layers are flat, because they exhibit this shape. All right. So that's a really good example of when that happens in real life. Okay, so there's what we're going to move on to now. So in the next bit, we're going to look at the word that you know to use for this substance, diamond, here, where each carbon is making 4 bonds. And I know you can't see this very well on the video, but you know from GCSE that we call the structure around a carbon tetrahedral, and that's because it's got 4 pairs of electrons and they move to positions as far away from each other as they can, and that's where you see it. Okay, and then one final sort of way to see this quite nicely is this model here, which has got it all tetrahedral like that. You can see that shape. So that's what we're about to move on to now. Let's do that then. So tetrahedral. And this is when we've got molecules like, and they're all going to be very similar whenever you've got something like this. So you all know how to draw the Lewis structure, and I'm going to draw it with dots and crosses rather than lines. For methane, I could have drawn it like this as well, and if it's 2-dimensional, we draw it flat, don't we, like that? But that is a misrepresentation of it, really, and we'll learn to draw 3D structures later on. You need to do your best to copy it's as close as you can to my best effort at this. So something like that. That gives you an idea 3D what tetrahedral looks like. The justification of that is exactly the same. All that is this. So one pointing towards you, one pointing away from you. That's all that is. The justification for that, I'll give you a chance to catch up and then we'll go through that. So the way we justify it is exactly the same approach as we've done before. So what's the first thing we count, please? Someone? Yeah, number of bonding pairs. So count them up. 1, 2, 3. So I'll say 4 bonding pairs. Next thing we count is what? Lone pairs, so 0 lone pairs. Next thing we do is tot them up. We say there's 4 electron domains. Don't skip any of this out in an exam, we'll get all of it. We're going to do fine. If it's got 4 electron domains, they move as far away from each other as they can. And again, we need to use this language. I think I might have missed it out on the trigonal planar one, but they move to positions of max SEP, or if you like, or minimum repulsion. Get into the habit of saying that every time in the exam and you'll get all the marks. And that gives it a electron domain geometry, and because there's no lone pairs, and a molecular geometry is what we call tetrahedral. And the HCH bond angle, I want you to learn this number. It's 109.5 degrees. If you say 109, you'll get away with it, but let's learn 109.5 degrees there. So that's what a tetrahedral structure looks like. So I'll try to come up with a couple of other examples of that, but they're all going to be very similar to this one, really. I'll give you a chance to write that, and then I'll do another example for you. Another example of this would be basically any molecule that's got kind of a carbon with 4 things coming off it. Diamond is another good example. But one we saw yesterday for the first time was a substance that's got a dative bond. We learned how to draw ammonium, which has got a dative bond there between the nitrogen and one of the hydrogens. Everything's the same. We've still got 4 bonding pairs, 0 lone pairs, 4 electron domains, and then 109.5 degrees, tetrahedral, and all that stuff. All the stuff I said before, tetrahedral, everything's exactly the same. It's another example of when you can see it. Remember we said that a covalent bond and a dative covalent bond, as far as the substance is concerned, as far as the ammonium is concerned, they're all identical to each other. It's just a way of us accounting for where the electrons have come from. Right, so we're going to change it up a tiny bit now, make it a tiny bit harder for the last sort of little bit. And we're going to consider molecules that have got lone pairs as well. And we're going to start with ammonia. So trigonal, these are, again, you're going to have to learn this shape. So trig on now, referring to the fact there's 3 things coming off it. Pyramidal. In other words, they've got the shape of a pyramid. And I'm going to draw that for you, just so you can kind of see what it looks like. And I'm going to end up looking like that. And if I take my model, although, where's it gone? There we go. And it looks a lot like, this is methane, the tetrahedral structure. If instead of the carbon here, this was the nitrogen, and instead of a hydrogen here and a covalent bond, this is a lone pair. More or less, it's exactly the same, right? It's just so that's the bottom part, ignoring the lone pair. That's a pyramid. So we say it's got a pyramidal shape. But I'll tell you how to write this up in an exam. I just want you to have a sense of what pyramidal looks like. So the kind of fun thing about this is that lone pairs and bonding pairs aren't exactly the same. And so I'm just going to cover this to start with, and then I'm going to move on to what it is you write in an exam. So if I'm going to just get a different bit of paper now, just to make this point. One way to represent methane might be with those pairs of electrons looking like, a bit like in the model that I sort of briefly showed you, like this, sort of like these regions of electron density, these white regions here, where the electrons are. They're sitting in that region. We'll come to that a bit more next year. So we've got regions that are like sausage shapes, and I'm not very good at drawing these, but we've got 4 lots of sausage shaped electron domains, and they're all the bonding domains. They move like that. And that, what's going on there, you've got a pair of electrons that are existing in that whole space. And they're pulled somewhat in one direction due to the nucleus of the hydrogen, and they're pulled somewhat in the other direction due to the positive charge of the nucleus of the carbon. And so that pair of electrons is smeared out into that kind of sausage shape. Negative electrons are pulled sort of outwards. Again, I'll just show you this one here. Perfect example of what that should look like would be this bonding domain here. But lone pairs don't look like that. Lone pairs are not being pulled by one carbon. They're not being pulled by 2 nuclei. They're only being pulled by 1. And so if I were to change this into ammonia, do everything else kind of the same, that's a bonding domain sausage shaped, bonding domain sausage shaped, bonding domain sausage shaped. But the lone pairs are only being pulled by 1 nucleus, and so they're a bit fatter, right? So they take up a bit more space, and that changes not the overall shape. It still looks very similar in terms of shape, but it just causes there to be a bit of a push downwards, and it's going to change the angle around these. So instead of being 109.5, they get squished down by a couple of degrees, down to 107 degrees, right? So that lone pair is just taking up more space. It's just a bit fatter, and just pushes the other ones down a little bit, okay? So that's my kind of attempt to explain it. What we'll do is now write what you'd write in an exam. If I can find my page, I think I'll start. Yeah, I started it here. So trigonal pyramidal. So what we do exactly the same process. We count up the number of bonding pairs. How many bonding pairs are there? Show me with fingers, please, everybody. Yeah, we've got the idea then. That's good, making sense. So 3 bonding pairs. How many lone pairs are there now, please? Yeah. Pairs. How many pairs are there? Yeah. So 1 lone pair. So how many in total electron domains are there, please, with fingers? So we just add those together. We've got 4. Let's try that again. So 1 lone pair, and a total of 4 electron domains. And that means the electron domain geometry, if I use this as kind of an example, is exactly the same as before. So electron domain geometry is therefore equal to tetrahedral. It's not changed. Tetrahedral. There are 4 electron domains that move as far apart from each other as they can to the tetrahedral. But when we talk about the molecular geometry, or the shape of the molecule, instead of including the lone pair, we ignore the lone pair in the shape now, and we say that it's trigonal pyramidal. But what we also need to be able to do is to justify that perfectly. So let me just get another bit of paper and we'll justify that. So, well, let's first of all, let's do it this way. So just like before, we say the pairs of electrons move to positions of max separation or minimum repulsion. It's getting boring writing the same thing every time, but then when you don't write it in an exam, you can't blame me then for not telling you or making you practice it. We will practice it on your own as well. So pairs of electrons move to positions of maximum separation or minimum repulsion. But the extra detail now we must add when we've got lone pairs is that lone pair to lone pair, let's try that again. Lone pair to lone pair repulsion is greater than, and that will become important in a bit, lone pair to bonding pair repulsion, which is greater than bonding pair to bonding pair repulsion. In other words, the lone pairs take up more space and they push harder against things. So in this case, we're noting that the lone pair bonding pair repulsion is greater than the bonding pair repulsion. And that means that the HNH bond angle is equal to, if you knock off 2.5 degrees every time there's a lone pair, you'll be good enough. IB, so it's 107 degrees. So if I look back at that picture up the top here, that bond angle is 107 degrees. It's just been squished down by a tiny bit, right? And I'm going to write another example up, which would be, yesterday we learned how to draw the hydronium ion. That would be exactly the same, trigonal pyramidal. For exactly the same reasons as before, identical. Right, pause this, let me get that done. Next example we're going to move to is when we've got molecules like water that have got 2 bonding domains, we've got 2 lone pairs. You end up with molecular shape like that, which is why I always draw water. That's why I always draw water like that. And we're going to explain that. It's exactly the same as before, though we're getting really bored and used to the way that we write these, but you'll be really good at it. Okay. So we're going to call these bent or V-shaped molecules. Okay, we're talking about the shape around the central atom. So the example we're going to use to start with is water. You all practiced this yesterday. You know how to draw a water molecule like that, or like that. And I'm drawing it deliberately with that shape because I know it's that shape, but we've got to justify it in that and explain it now. And that bond angle there we'll learn shortly. Now, if one lone pair took it from 109.5 to 107, what do you think this bond angle is likely to be? 104.5. Well done. Quick maths. Very good. So we'll learn how to explain that. So we're going to say, let's work through it together. Let's do a little bit of, I'm going to pause the video, do a bit of verbal stuff, and then we'll write it down. So 2 bonding pairs, you said, you're right. 2 lone pairs, you said you're right, leaves 4 electron domains in total, 1, 2, 3, 4. If we've got a 4 electron domains, it's tetrahedral because the electron pairs move to positions of maximum separation. And that means you end up, if you only look at the shape of the molecule, ignoring the lone pairs, we end up with the bent or V-shaped structure, right? But again, the explanation, just like before, is identical. So pairs of electrons move to positions of maximum separation and minimum repulsion. Lone pair to lone pair repulsion, or was it that wrong, is greater than lone pair to bonding pair repulsion, which is greater than bonding pair to bonding pair repulsion, which is why we end up with an HOH bond angle, which is less than before. In other words, the lone pairs squish them together a little bit more, is equal to 104.5 degrees. And if you were to write something similar to that, but not exactly that in the exam, like 104, you'd probably get the mark. All right. Now, when I share slides with you, you'll notice there's some funky examples in there, but essentially, if you stick to the rules that I've set you and don't worry about the examples on the extra examples on the slides, you'll be good. And what we'll do in a following lesson is practice this with these examples and some others, and that's where we're at. I've also got I think, just a few moments at the end for you to try a couple of them. Can you try these on your mini whiteboards? Hold them up, and then once we're done, we can all go. So I want the shape of that one, that one, that one, that one, that one. That'll do. We'll try those, and then we'll go. To tell you the answers, you worked out this one is trigonal pyramidal. Some of you worked out this one's tetrahedral. If you drew this one, you'd realise it's just like the one I drew before, which is trigonal planar. Another trigonal planar one is BH3. A tricky one, the end that we'll do next time, is that one there, which is linear. Okay, well done. I'll see you next time.